This lecture is about the differences between batteries and capacitors, as well as the similarities. And we'll also talk about capacitors in series and parallel, just like we did with resistors. Now, batteries and capacitors do something pretty similar. That is, they both store electrical energy, and when placed in a circuit, they provide that electrical energy in the form of a voltage that pushes some current around the circuit until they run out of electrical energy. One difference is that with batteries, the voltage remains roughly constant during discharge. So a AA battery should maintain a voltage of 1.5 volts for most of its life, roughly 1.5 volts, until it starts getting low, and only then will the voltage start to really drop off. Capacitors, on the other hand, they have Q equals CV. So what this means is as you drain the charge, Q, you also decrease the voltage. Another difference is that batteries discharge slowly. If you try to short out a battery, it won't just discharge instantaneously. Instead, the voltage it provides will drop substantially because it just can't drain so fast. Capacitors, on the other hand, if you short them out, they'll discharge essentially instantaneously. Batteries, they harness the power of chemistry to have much more capacity than capacitors, which essentially are just cramming electrons into a small space. Batteries use chemistry. Batteries have a long shelf life. They can sit on a shelf in packaging for years, some of them, depending on which type of battery it is. Whereas capacitors will slowly discharge if they're left alone, usually in seconds or minutes, depending on the type of capacitor. Some types of capacitor can last longer if they have a very high capacitance and a very good insulating dielectric. Batteries are complicated. This is another because chemistry. What do I mean by complicated here? The rate at which they discharge and how long they last is dependent upon the temperature, for example. Their capacity is dependent upon the rate at which they discharge. Also recharging them. Not all of them can be recharged. They have to be recharged at a particular rate, and sometimes recharging them the wrong way or discharging them too much or not enough can actually damage the battery. So just batteries, really complicated, and different types of battery chemistry have different complications. Capacitors, on the other hand, are simple. A capacitor can be charged and discharged tons of times. It doesn't wear out or anything like that. They're pretty much independent of what's going on with the temperature. Not completely, but they're a lot less sensitive to temperature than batteries are. So while they both can be used to store electrical energy, for different types of applications, you usually want one or the other, depending on what you're doing. Now, one example of using capacitors and batteries in a similar way comes up in solar-powered watches, and I can't remember what the relevant brands are and which ones do which, but some solar-powered watches use a capacitor, but other solar-powered watches use a rechargeable battery, and that's a case where it's kind of borderline which one is more appropriate for the application. But either way, in a solar-powered watch, basically what you need is you need to store electrical energy overnight. You need to store enough to keep the watch running, and you can do that either with a battery or a capacitor. Two different ways to store electrical energy. Speaking of stored energy, the potential energy stored by a capacitor with capacitance C and voltage across it V is equal to 1/2 CV squared. I find this form of the potential energy easy to remember, and that's because it's similar to other forms of energy we've dealt with before. Remember, kinetic energy, 1/2 mv squared. Spring potential energy, 1/2 kx squared. Rotational kinetic energy, 1/2 I omega squared. So lots of energies come in the form 1/2 blank blah squared. So we can write the potential energy of a capacitor as 1/2 CV squared. And that's the form that I find easy to remember it. Of course, you can use dimensional analysis to verify that the units are correct. And by the way, if you want to derive this, basically what it's coming from is the fact that as you charge up a capacitor, the voltage increases proportional to the charge, and the total energy then is the area under this graph. That's because for each little piece of charge that you cram into the capacitor, okay, the amount of energy that it takes to do that is the voltage times the charge, because remember, voltage is joules per coulomb, charge is coulomb, so you multiply the voltage by the charge, and that gives you the joules you need to cram it in there. And so that's the little piece of work that you have to do. Now, the more you cram in, the more the voltage increases, so that's why you have to total up all of, initially you're not doing very much work to cram a little bit of charge in, but as the voltage increases, it takes more and more work to cram some charge in. So the more charged it is, the more work has to be done, and so the total work has to be done winds up being the area under this triangle. And of course, the area of a triangle is 1/2 length, or 1/2 base times height, and if you work it out, you wind up getting exactly this expression. Alright, we're going to talk about capacitors in series and parallel, and what I'm going to do is I'm going to derive the equation for the capacitance of two capacitors in series, and then I'm going to give to you for homework the task of deriving the same equation for two capacitors in parallel. So basically we have two capacitors with capacitance C1 and C2. Because Kirchhoff's law, the total voltage across these two capacitors is the voltage across one plus the voltage across the other. Applying the law for capacitors, Q equals CV, we can replace V1 and V2 with Q over C1 and Q over C2. Now, why have I let the two charges be the same? That's because basically this piece of circuit in the middle, in between the two capacitors, starts out electrically neutral. So if this capacitor C1 gets charged up with plus Q and minus Q, then the top plate on the lower capacitor must have exactly plus Q to counterbalance the minus Q. And so that means the lower capacitor must have exactly the same charge, plus Q and minus Q. Put another way, any electron that leaves this top plate of the lower capacitor to give it some charge plus Q must travel to the bottom plate of the upper capacitor to give it a charge minus Q, because there's nowhere else for it to go. Anything that leaves here goes there. So the charges here and here are equal and opposite, so the charges on these two capacitors are the same. The total charges on each capacitor are the same. Now if we want to treat this voltage as the voltage across a single capacitor with an effective capacitance C effective, then what do we get for C effective in terms of C1 and C2? All these Q's cancel out, leaving us with this expression for C1 and C2 in terms of C effective. Really expression for C effective in terms of C1 and C2. Note that this looks similar to the expression for the effective resistance of two resistors in parallel. But here, with capacitors, this is the expression for capacitors in series. So, capacitors in series do kind of what resistors in parallel did, just in the way that the expression looks a little bit algebraically similar. So this was really a sample problem. This was a solution to the sample problem. A sample problem that says, show that the effective capacitance of two capacitors in series is given by this expression. And we solved this problem. We showed what was asked by considering two capacitors in series, using Kirchhoff's law to write an expression relating the voltages, and then replacing the voltages using the law for capacitance and deriving this expression using some algebra. Another step was to actually relate the voltage to an effective capacitance using the law for capacitances. So, now for homework, you'll do the same thing except with capacitors in parallel. So I think that this is problem 3. Show that the effective capacitance of two capacitors in parallel is C effective equals C1 plus C2. Now, like the previous one, you can do it. You have to consider two capacitors, this time in parallel. Use Kirchhoff's law to figure out a relationship between their voltages, and then use the law for capacitance to write that in terms of their capacitances. and also to relate their voltage to an effective capacitance. Now, a couple of things to note about this. First of all, this looks a lot like the formula for the effective resistance of two resistors in series. So, interestingly, capacitors in series had a formula that looked a bit like the formula for resistors in parallel, but capacitors in parallel have a formula that looks a bit like the formula for resistors in series. Just an interesting thing to note. Another thing to note is that there's kind of an intuitive explanation for this. If we think about two capacitors in parallel, and imagine that these are both simple parallel plate capacitors, then each one, let's say they're identical parallel capacitors, and let's say, well, they don't even have to be identical. Let's say that they each have some area, though. If they're simple parallel plate capacitors, then those plates have some area. And remember how the capacitance relates to the area of a parallel plate capacitor. It was equal to 1 over epsilon naught A over D. So, the thing is, now this top side, right, the two top plates are connected together of area A1 and A2. So they kind of behave like a single plate now, with area A1 plus area A2. It's got all this area plus all this area, and it's a single plate because they're connected together. So it's almost like there's an effective area A1 plus A2, and since capacitance is proportional to area, the effective capacitance winds up being C1 plus C2. So that's kind of an intuitive explanation for it. But anyway, in the homework problem I just gave, you'll derive that result using Kirchhoff's laws and the law for capacitance, and some good thinking about what the total charge is of this big effective capacitor plate in terms of the charge on this little plate and this little plate. Anyway, onward. This is the final and I believe fourth homework problem. Consider the following four capacitor networks, each containing 3 identical capacitors. All of these capacitors are the same. And rank these in order from greatest capacitance to least capacitance. That is, greatest effective capacitance to least effective capacitance.